Discussion of what maturity is and what it could mean for an organism. And as Mike said, I did start in 2009 in this laboratory studying radionuclides and how this affects metabolism of organisms. And the first animal I ever really studied in great detail was zebrafish. And so something which is interesting to know is the idea of heterochrony and the idea that variations in development can be important for evolutionary theory. And if you want to study heterochrony, it's important to distinguish between the time that you spend in a particular stage of development and the rate of growth within it. So if you take a zebrafish embryo, for example, in the very first part of its development, it has a growth rate of 3 millimeters per day. And if you go a month later around metamorphosis, at high food, it's 0.6 millimeters per day, and at low food is in the order of, I have some notes. Yeah, in the order of 0.3 millimeters per day, and the growth rate is continuing to slow down all through development. There's also the study of heterochyry. So this is a paper by Spicer and Berggren in 2003, but in the laboratory by Berggren in Texas, they do a lot of studies on how physiological regulatory systems are related to each other. So in here, the study is about how the sequence of developmental events relates to arriving at particular milestones in systems. So for example, when you're a developing embryo, is your eye developing at the same rate as your heart? If you have a small uncoupling of something in your heart rate development, does this change something else further down the line? And so their staging atlases are basically observations on organisms and morphological milestones where a set of physiological regulatory systems are assumed to have been taken place, and this corresponds to this particular developmental milestone. It's noteworthy that you can reach a particular stage in a staging atlas at very different sizes. So somehow how you're developing is uncoupled to how you're growing, and typically the range of sizes that can be observed at a particular developmental milestone increases as we move forward on the developmental arrow, so to speak, to not use the word time or age. And depending on the taxa we study, the size range at a particular milestone can also vary. And of course, not all taxa have very detailed staging atlases. But there is one for zebrafish. In 1995, there was a staging atlas which was published by Kimmel and company. And so here you have very, very specific, I have a pointer, very specific stages. And then it doesn't matter what size it is or what the time is. You can always relate things to these stages, and then the actual time is not super variable. And then later in 2010, they extended this to an atlas that goes all the way to the adult stage. And so birth in Deb theory more or less corresponds to PSB+. So there's a lot of details that go with each one of these stages. So in this case, the gut is in complete contact with the environment. This around here, we have this metamorphosis. And I guess this would be a puberty in the Deb framework. And I parameterized a full Deb model to lots of data on zebrafish growth and reproduction and development and anything I could get my hands on. In addition, some experiments I did which where I measured some growth and reproduction, and we're all very familiar with the DEB scheme, so about juveniles and adults no longer allocating to maturation but to reproduction, and I got these DEB parameters for the zebrafish. I got a lot of questions during the course. What do I do now that I have DEB parameters? And I can tell you some of the things I did. I also had the same question. But first, come back to to a slide that Bas made for a long time now, and it's in the micro lectures. And basically, the question here is, if such a large part of the adult budget of the Daphnia is allocated to reproduction, then what was the juvenile doing? Because there's no big jump in ingestion or in growth at the moment that reproduction is starting. The reproduction starts at 2.5 millimeters, so that's about, where is it? About here, so still a lot of growth going on, and suddenly there's all this reproduction. So the question could be, as it's put on the original slide, where do the resources for the reproduction come from? Or alternatively, where did it all go for the juvenile if the juvenile had this same flux? So maturity came as a state variable with the idea that it's work linked somehow to putting in place all of these regulatory systems. And you have maturity maintenance as an energy sink with the idea that if you don't eat enough, it's possible that you don't reach puberty. And without maturity maintenance as an energy sink, you would always reach adulthood and always be reproducing. So the parameter values I got for zebrafish, they allowed me to make some calculations. I think the egg size must be between 1 and 2 joules. It's 1.6 like this. For a 1 joule egg, so on the smaller size range, I calculated that at birth, what fraction of the reserve was used for each one of the processes as defined by the standard DEB model. And with this parameter set at birth, then 48% of the initial amount of reserve dissipated as work linked to maturity. I have 11% reserve left. I have 20% structure. This is this overheads of growth would be 9%, and then somatic maintenance and maturity maintenance. And I thought, oh, that's quite a lot to be dissipating as maturity work. On the other hand, the zebrafish is reproducing a lot, it's making a lot of eggs, and the flux which goes to maturation as an embryo or a juvenile is routed directly to reproduction as an adult, and these things are making a lot of eggs. But I thought I could add something to a typical zebrafish life cycle with this new thing. I could add here the cumulative joules to reach each stage, with the idea that even though maybe the size at birth or at metamorphosis, here I put it's about 1 centimeter, it's already between 2 to 3 centimeters at puberty, but here the information would be that you pay in cumulative amount around 20 joules, and then you reach metamorphosis, and then cumulative amount of joules after you pay 2,000, and then you would reach puberty. And in fact, I could take this whole post-embryonic staging atlas, and with my parameter values, I could calculate for each developmental stage, for 2 food levels, what the size would be, what the age would be to reach that. So for example, this here is around metamorphosis, and so it's about 18 days at a low food level and 13 days at a high food level to reach that particular stage. And then I was thinking that this maturity level is, as a kind of an absolute amount, is perhaps a much better quantifier for a developmental stage. But still, when I was thinking about it, the development of the zebrafish is taking place, between 4 and 5 days. And that's going quite fast, and the egg is anywhere between 50 and 80 micrograms, and then I'm saying that I'm losing 30% here and 20% there, and I didn't really have super exact measurements, and it's a lot of indirect ways. It's a very primitive version, first version of the Add My Pet exercise. And then I was at the DEB course and symposium in 2011, and I met Mike Kearney, and he said, you're doing these respiration calculations, maybe I can introduce you to someone who wants to do this for some frogs. And I thought, oh, that's a very nice introduction with Casey Muller, and she's working on then 2 species of frog, Pseudophrene bibroni and another species called Crinia georgiana. And the thing is, these things develop much slower, and also it turns out that people working on frogs have a generalized staging atlases. And so then the idea is that Gosner in 1960 observed frog development from the beginning all the way to the metamorphosis and made these stages going all the way to 48. And then, depending on what species of frog you're working on, you can always relate these stages of development to these Gosner stages. And then you can study how size and age at particular milestones varies across species as well as within a species, like what I was doing before. And so Reiss in 1989 stressed, so in relationship to the study of heterochrony, that we need this quantifier for internal time, which is independent of morphological and chronological criteria, because these things are very environment dependent. And so in that sense, it was useful to use the maturity here to study the problem of these 2 frogs, which was that starting with eggs of about 70 joules, so here was 70, the zebrafish was 1 to 2, so 70 joules, and here we have the stages against age that Casey measured, and you can see that this Crinia georgiana is metamorphosing much faster, and the problem was to study what was the energetics behind this. So what was the difference in terms of energetics of Crinia georgiana that would allow it to develop so much faster? And there was a large number of very precise measurements of bomb calorimetry at the beginning and at birth and at metamorphosis, yolk and embryo dry mass after, during the larval period, stage, time at each stage, dioxygen consumption against time and stage. And so we fit the Deb model to all of this simultaneously for both species. And the fits were quite good and allowed for some calculations. You can see on the online Add My Pet database all of the fits in addition for 2 other frogs. And we calculated these pies. And so basically what we did here is we can calculate, so we have predictions for dioxygen consumption against time and stage. And what we do here is we calculate the cumulative dioxygen consumption during this embryonic development. And at the end of that, we make a pie chart and say how many moles was consumed for each process. And we can see here for the embryo development that it's about 70% for growth, 20% for maturation, and 10% here for somatic maintenance. And if we go and say now we want to look at the cumulative dioxygen consumption over the whole period all the way to metamorphosis, and you have here this Crinia georgiana and then Pseudophrene bibroni, you can see that the maturation and maturity maintenance, well, 36% of the 29%, sorry, and 36% of the cumulative dioxygen consumed over that whole period was for work linked to maturation. And I thought, wow, it's a rather, important part of the budget. And in fact, as a side note, I was even surprised to see that overheads from the growth and overheads from the assimilation were also not so small, and I don't think this is necessarily, these values are to be trusted down to the micromole or something, but it is interesting to see that and worth further study, because in reality we very rarely have data and methods which allow us to quantify these type of overheads. So the really fascinating thing about Crinia georgiana and Pseudophrene bibroni, still to come, so Pseudophrene bibroni fit, the standard Deb model fits very well to Pseudophrene bibroni, and a lot of the measurements are captured very well. But there was a big problem for Crinia georgiana, And the problem was that as the embryo develops, there comes a point always where the embryo development slows down, and the interpretation with the Deb theory is that the reserve density is decreasing and decreasing, and then you really need to wait to start assimilating for the whole growth and everything to pick up again. And this is when everything should be slowing down for Crinia georgiana. And just at that moment, there's this huge increase in respiration rate. And I was wondering where that comes from. So with the Deb model, you have energy going into each process, and now suddenly you have this huge consumption of oxygen right at the moment when your reserve density is slowing down. And even if you play with other parameter values, if you say increase the energy conductance, it will increase your respiration, but it shortens your embryonic development. So it was very hard to find out where this came from. And at some point, we realized that you could get this increase in dissipation by assuming that that 1 minus kappa, so all of that energy that goes towards maturation, starts to increase for some reason in embryonic development. And how it works is that for an embryo, this entire 1 minus kappa branch is dissipating. And so by decreasing the value of kappa, and so increasing the flux in this branch, even though you are slowing down in reserve mobilization, you can get a big increase in this dioxygen consumption. And so that was the hypothesis we had, was that midway through development, C. georgiana starts to invest much more in maturation, and this shows up as this increase in respiration. And so the thing is that frogs, there's some direct developing frogs that stay in the egg all the way till they metamorphose. Crinia georgiana doesn't do this, but it's a facultative feeder after hatching and lives in these temporary pools, and the water level of the pool starts to go down. And it turns out that C. georgiana leaves the egg a little bit before actually being born. And that's that moment when it starts to rapidly increase in its respiration rate, and that this development is accelerating. And so the idea we had is that maybe it's linked to being in temporary pools, and then depending on what happens, you really need to be ready to hop out of the pool on time. So with these two studies, I want to come back to the idea that, Reiss 1989 put forward, that there was a real problem in analyzing heterochrony, because we needed some sort of metric for developmental time. And he put forth 7 criteria that such a metric should respect. And the first one is it shouldn't depend on the morphology. This is something which it should be independent of the body size. It should depend on one event. It should be unaffected by changes in temperature. It should be similar between closely related species. It should increase with clock time and be physically quantifiable. So I think that the maturity is a very good candidate for such a metric, and I think show that it is quantifiable on the basis of data, albeit by indirect methods. And so I kind of come back to an overview with it. When you're using Deb theory to analyze data, reserve is a very good quantifier for metabolic activity, because the rate of the mobilization is going to influence a lot metabolic rate. But how this is coupled with development is not so straightforward. And in that case, we have maturity as a quantifier for energy invested in, into development. When we modify the energy invested into one process without affecting growth, and we're changing respiration, but also the timing of key life history events. And I think this has a very important link with ecosystems, because the flexibility the organisms have to go through these different life history events is quite important, and that we can understand this with mechanisms, I think, is also important. There's some constraints for metabolism. If we think of it as as metabolism, this kind of biochemical machinery and all these reactions happening, and it has to conserve mass and energy, and it's perhaps quite essential that we pay our somatic maintenance costs, else, you know, we have to shrink or we will die. So there's a homeostasis and not so much flexibility on some parts, but other aspects of metabolism, and I think namely that related to maturity, is quite flexible. And you can get a lot of metabolic flexibility by somehow playing with what you're putting into maturity, or you're starting to reproduce. And so I would like to now discuss a little bit about, or spend the rest of the talk actually, discussing about metabolic flexibility and how this relates to the maturity concept. I studied, when I came to Marseille, I was here to study this Pelagia noctiluca, and it's a holoplanktonic cyphozoan jellyfish that's found sometimes stranding on the beaches here. And it was a real challenge because there was not much data on this species. So in 1997 or 1998, there was a very nice book written about cyphozoans, and the growth curves are very sigmoidal and usually reconstructed from the field. But maybe in the aquariums they're having good growth curves, but at least in the literature, growth curves of jellyfish under controlled conditions are very rare. And so I ended up with a lot of embryo and developmental data on this species done by Italians in the Mediterranean. And on the basis of that, I was able to once again get quite good parameters. And also, it starts off as an egg, and then you have a development all the way to the ephire stage. And I was able to, again, get ideas on how much must be invested to be reaching each stage. It's very nice predictions for how the last stage relates to temperature, but there was also tables with the developmental stage and size that I was able to use. And it's nice to know here that there's about 60 millijoules in an egg, so that's less than the fish. And here we have about 6 millijoules in cumulative amount. So you would think, yeah, 6 millijoules is not very much compared to 60 millijoules. So maybe this is special. And what's to keep in mind, and so that's another coming back to what parameter values are telling us, is that Pelagia noctiluca has a really high reserve density. At least that's what the parameters and this analysis suggest. And so high, in fact, that almost of a fully grown maximum size jellyfish, the parameters suggest about 99% reserve. So at birth, when the reserve density at birth is equal to that of the mother, most of this guy is reserve material. So the 6 millijoules isn't directly interpretable to say it's a lot or not a lot invested in metabolic processes. So it's important to compare. Aurelia aurita is another jellyfish. I don't have parameters for it, maybe one day, but it goes through this polyp stage, and it can sometimes undergo direct development, in which case the egg, there were some very old studies where they observed this, and it has to do with, during the early stage of egg development, it goes one way or another way. I think it's like the evagination or invagination during the gastrula stage, and then it can just directly go to being a free-living adult. So the flexibility is really amazing, and I would think that maturity would be useful for being able to capture this. I studied in some detail with Lodewijk and Henk van der Veer and Jean-Christophe and others this comb jelly. And to give an idea that, and a lot of the metabolic flexibility wasn't so much in changing how the organism invested in its maturation, but had to do with the timing of starting its metabolic acceleration. But what's interesting here is I again drew graphs of budgets. But the first one I showed was a pie chart of how much of the reserve in the egg was invested in different metabolic processes. And that's pretty straightforward. An embryo doesn't assimilate. And then I gave charts where cumulative dioxygen consumption for each process was presented. And here is different. I represent what's mobilized from the reserve, so it's snapshots. I imagine that I'm taking a picture of this comb jelly during its larval stage, so before it starts off with long tentacles, which will be resorbed into the lobes. And I start here with a snapshot much before lobe formation. And then I calculate how much is mobilized from the reserve, and then I take a snapshot, and 61% of that mobilization goes towards growth. Part of that, most of that will be fixed in the new biomass, part of that is overheads, and 30% is going towards maturation, 9%, and again, these are not values to say it's exactly 9%, but it's an idea based on data which can of course be improved. And then I take another snapshot here at puberty, and in which case the organism is no longer allocating towards maturity, but is now allocating towards reproduction. So we see that the investment in growth is less, and that's because growth is saturating. Somatic maintenance is proportional to growth, so somatic maintenance costs are more important here already. And when we arrive at a fully grown adult, then there will be no more growth, and it will all be in somatic maintenance. And here we have 28% in reproduction and some small amount in the reproduction overheads. So again, this maturation is an important part of the energy budget. And we saw from the previous graph that an illustration that we already know it, but that how the organism is routing from maturation towards puberty. And there's an interesting case study of another comb jelly. This is Meretensium ovum, and there's a population of this species in the Baltic Sea, and they found out that it was only larval forms of the Meretensia ovum, and that all of the recruitment of this population of comb jelly was only through larval reproduction. And this is some people call it pedogenesis. And the idea, well, what happens is that a first set of gonads appears, and the organism starts to reproduce, and then those gonads disappear, and then it grows and continues its development, and then it gets its adult gonads, and it's a simultaneous hermaphrodite, turning out large numbers of very small eggs. And the argument here was that the thing stayed small, so then reproduction was favored over growth. And so you have a direct competition. And indeed, in the case of Crinia georgiana, with the change in the kappa value, like I showed, that there is somehow an increase in maturation at the expense of growth. But here they mentioned this an old study in 1972 by someone called Jed Hirota, who studied another ctenophore and he observed this in the laboratory and explained that this was the proof that you have this reproduction at the expense of growth. And I was visiting the NEOs, and they have this really nice old library, and came across the article by Jed Hirota in 1972, and this study on Pleurobrachia baccae. And so I digitalized the data, which look like this. You have this ingestion as function of time, and here in the little circles you have the observed growth, and it's one individual in a jar, and he has 3 such individuals in 3 separate jars. And here for this individual you have its reproduction. And when I fit the Deb model to this, I used the observed ingestion as input to the Deb model to see how it was capturing the simultaneous growth and development. And I thought that the reserve dynamics were quite good for capturing how changes in growth are smoother than the fluctuations in ingestion. There's also some small changes in the reproduction. This is not captured so well, but I do capture that there's no growth happening, and there's some problems with early ctenophore growth, namely that they increase in water content, and also that they might not have the same shape coefficient as later on. But I need to study this more, but I would say that I don't really need the assumption of a trade. I wouldn't say here that growth is limited because the animal is reproducing, I think it's explained very well by the fact that the organism hardly eats. And so an alternative hypothesis would be that the organism can switch between maturation and reproduction in this early stage, reproduce a bit, and then go back to maturing. And when you make a change here between allocating between maturation and reproduction, you don't impact in any way your growth. And the organism possibly can do this, and it would be interesting to study how exactly one goes from investing in reproduction to investing in maturation, and why it can be that an organism could play with those two. But somehow looking more closely at this, there's something else which appears a bit strange in the scheme. And that's, well, on this side I can understand really well that if you don't mobilize enough to cover your somatic maintenance, that you start shrinking. And I think, yeah, that sounds pretty reasonable. But then you notice, at least numerically, if you didn't think about this beforehand, that if you don't mobilize enough for your maturity maintenance, then your maturity is also going down. And then what happens? Do you start developing backwards or something like this? And then it turns out that some organisms do develop backwards. And this is a 1995 study of Turritopsis nutricula, and they document 3 different routes by which here you have this little, and he going all the way back to a little cyst, and then a stolon, and then becoming a little polyp again. And there's 3 different routes by which this organism does it, and apparently it can go backwards and forwards indefinitely without any type of damage. And there's no, the bioenergetics of this hasn't been studied. It has been studied from a developmental perspective. And it turns out that even here, in the tree of animal life, there are gradients in the capacity to do this. So the Aurelia aurita that I showed earlier, it was also observed to go backwards. Once it passed the ephire stage, a particular stage, and grows, they did starvation experiments, and it went backwards up to a point, and then it could not go backwards beyond that point. And after going backwards and forwards a number of times, Aurelia aurita becomes damaged. But to what extent this also relates to damage from the shrinking. And so depending on your parameter values, your shrinking or rejuvenation dynamics wouldn't always be coupled in the same way. There's a particular beetle, and this is written also in the comments of the Deb book, which has been observed to go backwards and forwards a bit, but also with some damage. So this is also a very interesting thing. So I kind of come to a close here, but the idea is that by studying eco-physiological data in quite some detail and parameterizing the Deb model to it, you get very stringent constraints as to where energy can be invested. And if you're saying that so much is involved in your assimilation and so much is in your overheads of growth and so much is in your reproduction, then you get constraints as to what could be in maturation, etc. Different data have different information levels, but whatever it is, the interpretation you come out, you end up with an idea of what the energy budget is and how it must be moving through ontogeny, and you come up with particular conclusions as to how organisms would be responding in shorter-term experiments. So you have 1 week to look at an animal or 2 weeks, and how does that relate to the life cycle of your organism? And if you are able to do very big detailed studies on embryo and juvenile development, then perhaps that tells you something about adult physiology, and perhaps that something is telling you something about how it might be reproducing. So I could see, for example, direct applications in fisheries and in increasing our understanding of how, say, a gonadosomatic index can be mapped to a reproductive output. And so I would finish with 2 quotes. The first one here from this paper, that we would do well to study the ecophysiology of taxa by comparing parameter values of an energy budget that's accounting for this interrelationship. And the moment we start changing our models for every organism in every context, then those parameter values don't have meaning when we compare them one to the other. And that lack of data is always going to be a problem no matter which organism we study. And then in this case, these predictions are better than no predictions. And they can serve to test the theory when more predictions do become available. Thank you.
Thank you, Starrlight. Can I indulge in the first question?
Yeah.
So there's an idea that perhaps the defense, the immune system could be part of the maturity contribution. You didn't mention anything about that. Do you have any thoughts on that? And I guess that's also relevant in the context of reversing your maturity level.
That's a very good question. When I first started reading, there was a study in 1995 where zebrafish was exposed simultaneously to low levels of some particular metal and also to pathogens. And the presence of pathogens or metals makes, they work together. And then I thought maybe this could be explaining that if you have not paying your maturity maintenance, maybe you become more susceptible. So it would maybe act more on the survival probability, but maybe it's facultative in the sense that if you're not paying it right away, you don't die. But I haven't seen any studies which quantify this in detail. So
an area for future research. Do we have any other questions?
Thanks, Starrlight, for this talk. I was fascinated by the cumulative investment in development of the two frogs.
Yes.
You compared the proportions in the different allocated to the different categories, but you didn't say anything about the absolute values. And if I'm correct, and I saw it correctly, one of the species spends about 5 times as much energy up to the same point as the other. Where does that come from? So
the absolute values?
Yes. So
are these dioxygen pie charts?
Yes.
Yeah. Let me close this. I think I put absolute values. So it's 9.7 micromole in absolute and 2.8 micromoles.
No, but it's the next one. The next pie chart actually. This one, because there you see that the right-hand side 40% is 900 micromole, and at the left-hand side, I can't exactly read it, but 21% is 70 micromole. That's quite a difference. If you calculate it, it's a factor of 4 to 5 difference. So where does that absolute difference come from?
The eggs aren't exactly the same size, and they eat. So they eat during that period, from birth to metamorphosis. They're eating, and so this is then.
But this is cumulative amount of micromoles.
Yes. So they don't respire the same amount. Both frogs.
But they are of the same size?
No, their sizes are also different. Their ultimate weight is different. So.
Okay.
The C. georgiana is much lighter and is hardly eating after birth. And this one, the Pseudophrene bibroni, is eating after birth, so is actually making more of itself. It's growing. And the C. georgiana is not growing, so.
Okay. Okay, thanks.
Hi, thank you very much for the presentation. So, how did you rule out that the sudden increase in respiration by C. georgiana could be, or Georgiana, sorry, could be coming from a behavioral change or some kind of movement that would also register as respiration, right? And possibly the second question, if you feel it's we have time. When you go back with maturity, you're actually utilizing energy to revert, I would assume, rather so. How does that bioenergetic then work out?
That's a really good question. The second one, I was wondering that too. How would it work out? I guess when it's a cyst, it doesn't need to pay maintenance or do very much when it's a small cyst. So maybe once you're down to the beginning, then you're not paying so much, and then you can just make your way back up when conditions are favorable. But yeah, I don't know how the going backwards would work out. For the first question, I think there was nothing special in that frog's movement. But of course, I didn't model explicitly movement. But when we were talking with Casey, she didn't see something very special, that it was, you know, really jumping around or doing something.
I could throw it, but...
Okay, thanks, and thanks, Starrlight, for a very nice talk. And I have a question, and I'm not sure that it's the same organism that Tin just now asked about, so I have the physicist's abstract way of looking at this, so this was just several things, several instances. But you had this, this example where you explained the acceleration in respiration as shutting down allocation to maturity.
Increasing?
Maybe if you can show, it's about somewhere halfway through.
Is this?
No. Well, anyway, so even in this one, you explain it as shutting down allocation to maturity.
As decreasing the value of kappa, and so increasing the flux in this branch, so increasing the allocation to maturity.
Okay, well, maybe I was getting it the other way around, but anyway, or maybe it was here and also in another place, but my point is, do you have any extra empirical test besides the original empirical pattern that you were trying to explain? You see my point? So the thing is, what I'm asking you is this is only an ad hoc assumption. If you're doing it directly to explain, it's like standard Deb model, kappa is constant. A non-fitting empirical pattern comes up, and then you say kappa is not constant. And if you do just this, that's an ad hoc assumption. So the thing is, you would need to have an extra empirical test. Even if you don't have it available, you should at least say what would be the empirical test, the independent empirical test that would allow you to test your hypothesis.
So
that will allow you to test this hypothesis.
It's a hypothesis, yes.
But what would be the empirical? So I mean, so you put this hypothesis, but the thing is, how would you test it?
Well, the lakes, apparently, the ponds, they're drying up more or less fast, and there was a study where the person was looking at how these frogs were developing with these ponds drying up. So I would think that some comparing how this works out in two different situations to see if indeed in one case it is doing this, and in another case it's doing it to a lesser extent, and then you would have to you would see if it indeed does this, and if it depends on the environment, and if it works out in this way for both sets of frogs in both environmental conditions.
But would that allow you to test that that's due to its change in allocation, change in kappa, or anything else?
Well, you at least, all the information you have is that the standard Deb model is not fitting, and that you have a deviation from the standard Deb model. And so you can see that is there a change in energy allocation to different processes by which you can capture this pattern. And so that's about what we can do with the analysis of eco-physiological data, and then perhaps more detailed work on how this works out in terms of organ formation, and looking more in detail exactly what the organism is doing. So there's a chapter in Casey Muller's thesis where she does light microscopy on resin, And so she observes in some detail how these frogs are developing, but it's difficult to link this to real changes in how regulatory systems are actually changing. That step is still missing, and it's still missing also for understanding metabolic acceleration, and that we can see in the morphology of how things are going on. That linking is still, I think, needs to be done.
Okay, thanks.
I remember when I spoke to Roger Seymour, who was Casey Muller's supervisor and did the initial work on this. He was really excited about the notion of depth theory because he'd been looking for a way that you could actually quantify the costs of development as opposed to the costs of growth.
Mm-hmm.
And I guess in any energy budget model, there's got to be some cost of development hidden in there. And I guess it would normally be in the costs for growth. And in the DEB model, it's partitioning it out in a particular way that you expect particular things because it's driven by the kappa rule. Would you say that's a fair description? So
Yes.
So one way or another, there has to be some implication of changing allocation to development, right, in the respiration. And the DEB model is saying something quite particular about what that should look like.
Yeah, and also it becomes difficult when you have a lot of different types of data sets. So here, the egg is an interesting system because there's no energy input in the egg. And then you have exactly, when the thing is born, then you have exactly 3 grams which are gone. And I say, where did those 3 grams go? And they actually leave, most of it is gone in the form of CO2. And it's really then fascinating to understand, well, then how much of that was for this and how much of it was for that. And then the number of scenarios onto how the energy could be partitioned, it becomes rather limited, especially when you have the initial energy content of the egg, the final energy content of the egg, the dry mass of the embryo increasing, the dry mass of the yolk decreasing, and the dioxygen consumption. So you don't have the CO2 production, and you don't have the heat here, but it is the 2 data sets are among the more detailed for doing mass balancing that I've had the honor of looking at.
So we still have a bit of time, yeah.
Maybe I can just shout.
They want it recorded.
Yeah.
You may not.
I know. Thank you. I was wondering with I noticed that with the frogs and with zebrafish and also with the jellyfish, you have around 30% investment into maturation and the maturity branch, which would kind of maybe be related to 1 minus kappa branch, which would make typical kappa around 0.7. And we have in the collection mostly, it's like the typical value is 0.8. So do you have maybe any comments on that?
Yeah, it's suspicious that I keep on coming on low kappa animals, I don't know. There's some, but yeah, this Pelagia noctiluca has a very low kappa. And when we look, it is exactly the value which is maximizing reproductive output. There's another paper by Lika and Bass looking at, so all else the same, you can see which kappa would maximize reproduction, and most of the species don't have that value. And Pelagia noctiluca and the zebrafish have the kappa value, which perfectly optimizes the reproductive output. Both of the frogs? Oh, I didn't check. They're not as low, but they're still pretty low. They're below 0.8. So, yeah.
Well, if there are no further questions, we're a little bit early, but I guess we just press on with the next presentation. And thank you, Starrlight.